Hello everyone, I am Mrs. Padmashri from SNS College of Engineering, Coimbatore. Today I am going to explain the topic of deep learning, in which I will be explaining the continuation of my previous lecture, which is called AlexNet architecture, one of the example of convolutional neural network architecture in deep learning. And in that architecture, I said we have RELU. Okay, so we are going to see what is this RELU in this lecture series. It is called a rectified linear unit activation function. So this is the before the development of AlexNet architecture, the deep convolutional neural network has a challenge, which is known as vanishing gradient problem. What is this vanishing problem? This has the use of sigmoid and tan h function. So first we'll see what is the sigmoid function and tan h function. Okay, mainly this has these functions, these two functions saturates at both positive or the negative values. It may be leading to the gradient approaching zero during the back propagation. Okay, so RELU, let's see why it trains faster with the RELU. We use this rectified linear unit to train the convolutional neural network. It has overcomes the drawback, and it has given by f of x is equal to max of 0 comma x. It is going to plot two function tan h and RELU. The picture that you are going to see, you're seeing now is a tan h function. See, the graph is plotted between the positive and the negative value, in which we have 2, 4, 6 in x-axis, and this side -2, -4, and -6, and the y-axis we have in the form of points 1.0, starting from 0.25, 0.50, 0.75, and the negative value here, the y-axis. Okay, so when you plot a tan h, see, you could see it is going to raise from the negative value to, and it goes back to the positive value. Okay, so this is a tan h function. And when you see RELU, see the RELU, which is here, it's not going to have any both the negative and the positive. It's a straight linear line. Okay, a straight line. It's a linear line, and it has only the positive value. So because of this advantage, the convolutional neural network follows this RELU, which is called as a rectified linear unit activation function, which is faced a significant challenge of vanishing gradient problem, and these functions saturate at both the positive or the negative value. That is going to lead a back propagation. So we all know that back propagation will be considered as one of the drawback in the neural network, since it takes time and it has to so when we did not get a proper input, or there is a error in the network or error in the input, we will back propagate the data, rectify those, then again transmit the same to the next layer. Okay, these are all the things we are doing. Okay, to overcome that, we have this rectified linear unit. Say if you use tan h function, which goes both the positive and negative, if we use RELU, which has a linear straight line. Okay, mm, so some of the example of tan h function, which saturates at very high or very low values of z. Okay, so the slope of the function, which goes very close to 0, you could see in tan h. See, the slope which is going very close to 0, touches the rises from here negative, touches 0, which very close to 0, then it goes to high value. So the tan h which goes close, very close to zero, this can slow the gradient, slow down the gradient descent. But if you see the RELU function slow is not close to zero. Again, I will show you. See RELU which is not close to zero. See, it is starting from here, the negative value, and again just it goes to zero and it rises. So which is not close to zero for higher positive values of Z. So this helps the optimization to converge faster. This is the advantage. And for negative value of Z, the slope is still zero, but most of the neurons in neural network usually end up having positive values. So the tan H, LRU, LERU, we can sorry, RELU and tan H. When you compare these two things, we could see some advantage in RELU only. So we are using RELU, rectified linear unit in convolutional neural networks. Okay, so the max pooling concept also I'm going to explain in this lecture. AlexNet network has a max pooling. So I said right, in the architecture only we see pool 1, 2, 3, 3 pooling layers. It's mainly used to reduce the size and the complexity of feature maps. It is generated by the convolution layers. It performs the max operation on small regions of the feature map, such as 2 into 2 or 3 into 3, and outputs the maximum value. Mainly max pooling was to reduce the size and complexity of feature maps generated by the convolutional layer. And the size may differ, right? 2 into 2, 3 into 3, and it outputs max pooling. It outputs the maximum value. This approach helps to preserve essential feature, which retains the essential feature, discards the redundant or any noisy feature. So the pooling, it mainly helps to retain the features, and it discards any noise or redundant. So thank you. The rest will be discussed in my next lecture.